As you guys can see, I have my own drink too. Um, except this one does not. I don't. I think it has the opposite effect compared to what Yoda is having. All right. So it is time to get started. There we go. All right. So it is 5:30. All right. So yes, this is the wrong stuff. Not for this class. Not for this class. And let's get back to the content of our class. So right now I have a lot of courses on my list because I'm helping to evaluate how other people teach their classes. So there we go. All right. So at this point, we don't really have any new labs, just because well, I can release a few more, so that you guys can get some additional, basically exercises, for working with structures. So I can go ahead and release these ones at the end of today's lecture. These are fairly easy, fairly quick. They are things that we have already talked about, but I just thought some additional treatment cannot hurt, right? Um, so at this point, I think it's pretty much kind of the other way around. If you guys have any questions, go ahead and ask those questions, and I'll try to use some additional sample programs to illustrate those concepts. All right. And then Omer posted, I wanted to clarify for the recursive lab when we have the following statement, x equals to f blah blah blah, and if we're to run x equals to f of 3, is this a valid approach? All right, so let's get to that particular statement, because how you want to test your code is entirely up to you, and you don't have to assign the return value to a local variable to test it, because we know it's going to be in register A, so that would be the easiest way to test your code without having to have a local variable for main. All right, so let me just kind of quickly get into the quiz itself, and I think it's probably the spacer that has the description. Nope, it's question number 3 then. Yep, there we go. All right, so your assembly language code doesn't have to be resembling the main function here. Instead, you can always just have main to call the subroutine, because you need to test whether your code is working or not. So you still need something to call the subroutine that you're developing. But when it returns, when your subroutine returns, the return value is in register A. So as long as you don't change register A before the halt instruction, all you have to do is to really look at register A and see whether it is the correct value or not. Let me see if I can let me see if that addresses Omir's question or questions. When in function, if we allocate space for parameter n, in function f n is asterisk constant. Well, I'm not sure what that means, but I can use a sample program to illustrate, how to pass, a parameter. So I'm going to use a, yeah, sure, absolutely. Oh, I know exactly what I need to do. I am going to turn the absolute value thing into a function. That sounds interesting, right? I mean, it should illustrate what it should answer the question from Omir, and also at the same time kind of remind you guys what is and AA, how to take the arithmetic negation of a particular value. We call that 2's complement. So yeah, let's do that. Okay. Well, I like these kind of impromptu assignments. When I was a student, and that was a long time ago, I used to go to programming contests. Basically, what they call hackathon these days, well, okay, it's not exactly the same thing. Hackathon is very unstructured, but programming contests, especially those organized by the ACM. So if you're not a member of the student chapter of the ACM of Los Rios, you should probably consider joining them unless you're graduating, because the ACM organizes programming contests. At least back when I was a student, and it really I find it very enjoyable to be assigned to some random problem to solve, and you're in a classroom and a whole bunch of other people are competing with you. The competition part, I don't really pay much attention to. I just kind of like to problem solve. That's all. All right, so let's go ahead and write the absolute value function in C first, right? Because this is what I have been doing is to illustrate how to do things in C, and then we'll do it in assembly language, standard integer. Okay, there we go. All right, so we have the function, and it's gonna return a int8 underscore t. We'll call it tax abs, and it will take an argument like that, and then here we'll go ahead and use my favorite, which is a ternary expression, to return the result. So we say if x is less than 0, we will return the negation of x. Otherwise, we return x itself. And here is main. And in main, well, okay, if I want to show you that this program does work, I can't really just call the function without storing it to something, because in GDB there really is a way to show what is in the register, but it's not. Well, let's give that a try. Okay, so let's give that a try and see if we can find the result that way. Alright, so I'm going to assemble this program, compile this program, run it inside GDB, and we'll see if it does store the representation of -3 in quote-unquote register A, but this time in the Intel 64-bit architecture using the AMD instruction set. There we go. Alright, so let's give that a try. There we go. All right. Oh, I forgot the -G option, which is needed in order to retain all the debug information. There we go. All right. So now we can just go ahead and run the program and put a breakpoint on line 11 and put a breakpoint on line 5, because I just want to make sure that it did go into the subroutine, because sometimes the compiler is really smart and it says, hey, this doesn't do a single thing. Why don't I just return 0? And not call tax abs. So we'll run the code, and indeed it went into the subroutine. Continue. All right, so now we want to take a look at quote-unquote register A. I cannot remember the name of the 64-bit integer that corresponds to register A, so I'm gonna list all the registers, and there are quite a few. I think there are about 20-something registers. RAX is what we want. RAX is the 64-bit version of register A, and it's not what you think it is, because you can see how the Intel architecture has A, B, C, D. So you might be thinking, Tech, you're just copying from the Intel architecture, because you also call your own registers A, B, C, and D. That is actually incorrect, because A stands for accumulator. I think B is base, C is a counter, and then D is, I cannot remember. D, there's a particular name for D. This is a modern processor, yes. So to answer Bernard's question, this is the 64-bit AMD instruction set, which I think is, as far as consumers are concerned, this is the current instruction set used by Intel and AMD processors. My processor is an i7, so it is specifically an Intel architecture, but they share the same instruction set, which is the AMD instruction set. I know how confusing that sounds, but that's that it has a long history, and I'm not going to spend too much time to talk about it. But the end result is yes. So register A does have a value of 3, which is correct, right? The absolute value of -3 is actually just 3. All right, excellent. So the C code does work. Now we're going to work on the assembly code. All right, so the assembly code, we're going to copy the C code, which is abs.c, to abs.ttpasm, and then we'll work on the assembly code, asb.ttpasm, and we'll do the usual trick, insert comments, on every single line, including the blank lines, even though it's not really necessary. And there are ways to detect whether a line is empty or not, and only do it to the non-empty lines. But I'm not going to even bother. I'm not going to bother to do that. All right, so there we go. And as usual now, okay, so this is something that I changed this semester, is to, well, in the middle of the semester, is to change the way we treat main. Okay, at the very beginning we kind of treat main as, okay, it's just an entry point and it has a halt instruction. But now we are actually treating main as if it is just a normal subroutine, because that's basically what it is in C and C++. Main is really just a normal subroutine, except the name is used by the entry code for the entire program, and it will call main, as the first function. So that's, from that perspective, I am trying to replicate exactly what a production C program would be using. The production C compiler would be doing, along with the linker. All right, so now we're gonna set up the call, which is ldia.6+ decrement d stda jmpi main, and when it's all done, it's time to do the halt instruction here. So I do want to emphasize one thing. I thought about how to help people do better in the final exam. So one thing is, at this time, you really should understand exactly what each instruction is doing. So all of the instructions that we use, you really should know what they do. Not so much how they get it done. In other words, if you don't really fully understand how the multiplexers and the demultiplexers set up things in the processor, it's probably okay, as long as you do understand the full effect of every single instruction. And if you think that you might have some knowledge gap about the instructions at this point, my advice is really get it all straightened out as soon as possible. So it's just a little bit of advice to people who want to do better in the final exam. All right, so this is main. Main has no local variables, so this time I'm not even going to bother to specify main LVS, and allocate and then deallocate. So what I'll do instead is I am just going to set up the call to text absolute value, and then do a return 0. So there we go. So we are going to do a LDIA with -3. That's the value that we need to push on the stack. Decrement D to allocate the space on the stack that we need to push the argument. STDA, that finishes the pushing of the -3 as the argument to text ABS. And then we set up the return address, which is LDIA.6+. So once again, the notation of .6+, you should probably understand it now, because in the final exam, you are going. It's likely that I'll keep the format of what I did in the previous semester, but the program is going to be different, and your job is to spot problems within that program and fix those problems. So knowing exactly what each instruction does is a prerequisite to do well in the final exam. All right, so LDIA.6+, decrement D to reserve the space for the return address, and then we push the return address, and it's time to call the subroutine, which is tax ABS. When it returns, we still have one argument sitting on the stack, so we're going to deallocate it by incrementing the stack pointer. So now, right at this point, okay, register A should have 3, okay, whatever the absolute value of the argument that we push on the stack. And then after that, main has to do its own return. So we set up register A to be 0 before we use the usual 3 bytes of the 3 instructions to get back to the caller, which is LDBD, increment D, and then JMP B. There we go. All right, so now we have to now go back to here, which is the main point of this sample program, is to illustrate the answer to Omer's question, which is okay. So as far as pushing is concerned, this is how we push the argument, and it doesn't matter whether we are doing this inside a recursive call or whether the call is not recursive. This is how we set it up. In this case, ABS is not recursive, so there's not much that we need to do inside ABS except to illustrate how we are going to get the parameter. Yeah, I had to think for just a little bit because I need to, in my head I had to differentiate between the term parameter, which is how we see things from the function being called, or argument, which is from the perspective of the caller. So in this case, x is a parameter because we are looking at it from the perspective of the subroutine being called, function being called. All right, so we're gonna do something here. So in this case, it is relatively simple. So I'm going to give you an alternative sequence of doing this. It would not be a very, it's not consistent with what I have been doing in the past, and it's intentional. The intention is not to confuse people. The intention is actually help people understand what is going on. Because if I keep using the same sequence of instructions to do exactly the same kind of thing, then people would just kind of try to rote learn and just try to memorize the sequence. But if I kind of give it some variations and just kind of say, okay, this is another way to do the same thing, hopefully some people would just realize that and go like, oh wait, how does this get the same thing done, right? So I'm gonna do exactly that. So this time I'm going to copy the stack pointer to register C because I can't really move the stack pointer up unless I am sure I don't need whatever the stack pointer is pointing to right now. So one question you might want to answer in your head is, what is the stack pointer pointing to on the stack right now at this point? Okay, so try to answer that question. But I'm going to move on and say increment C, and now we get to the value, we get to the address of the parameter in C, not D, C. I just said don't increment D. So I increment C, which was a copy of register D, but now they are different. C is now one more than what is stored in register D. And I'm going to do a LDCC. And I claim that register C now has the value of parameter x, which means I'm ready to go through all of this stuff here to figure out the absolute value. So if you still remember the absolute value lab, you probably still have that sequence in your head. So we're gonna do basically the same thing. And I'm looking at this code here and go like, that's gonna be, I'm gonna need an extra instruction later on. Let's not do that. Let's make it as simple as possible. So we're gonna use register A here, and I also remember that I need to have those 3 instructions to get back to the caller. So we have LDBD, increment D, and JMP B. There we go. All right. So on line 17, if you still have the code for the absolute value logic, you can just kind of slap here because in that specific question we were also using just register A. So other than how register A got its value, which in that particular program was from an LDI instruction, here we just say, okay, now register A has the proper value because we just got the value of the parameter. So now we just have to do an AND AA, and that will force register A's content, all 8 bits, through the ALU, and the sign bit and also the Z bit are going to be affected based on what A is. So that's another thing that you should also know by now, is what the AND AA instruction does when in this type of context. That one might require you to read inside, to investigate inside the ALU and find out, how the value going into the ALU, how it's going through the AND gate, and how the output of the AND gate is going to affect both the sign bit as well as the Z or the 0 bit. So that portion is inside the ALU of the processor. All right, so having said that, we're going to say JSI to some locations. So we'll say tax ABS, go ahead and negate. Otherwise, we don't need any negation, so we'll do a JMPI to the return code. So we'll call that label tax ABS return, and that label belongs here. Tax ABS return belongs here. And so the JSI is going to land here. So tax ABS negate. All right. So if we ever get to this point where the cursor is blinking, we need to arithmetically negate the value in register A, which is 2's complement. Now there are 2 ways to do this. You can always use a subtraction instruction. You'll put a 0 into some other register and then subtract A from that other register and then copy that register back into A. You can do that. Or you can do the 2's complement, which is doing a not A to take the bitwise not of A, which is also known as 1's complement. All of this stuff we have talked about already. So I certainly hope that you guys are retaining what you had already learned. I mean, the final test, the final exam is just like the other exams. It's open book and open notes. But if you need to look it up, during the exam, it's gonna take you extra time. Okay, so you just kind of have to figure out how to how not to spend extra time in the final exam to look up stuff. So that's something that you can work on. All right, so the next thing is we need to add 1 to the 1's complement. Now it becomes 2's complement, and we're done. All right, so this is the code, or at least I claim this is going to do exactly the same thing as the C code. And then we're going to go to River Spider. And once again, there were a few people asking about how to set up River Spider. If you don't want to do it, that's fine. You can always just kind of manually copy manually run the program inside TaxToy processor, which is inside Logisim, which is a Java program. Or you can go ahead and use River Spider. So it's entirely up to you how you want to do this. So here I just ran the program. Well, okay, I haven't run it yet. It's still in process. All right, so it thinks it's done. And let me look for the assembler tab. And I got a few. There's one that is private that you guys cannot see because I have to do some experiments with that one. So this is the one that you guys all can see. And yep, okay, I can see a few people are here already. Very good. One person is here already. I mean, before class, okay, we only got one more class on Tuesday. But at this point, most people would know that at some point in the lecture I'm going to use the assembler. So there we go. So this is the code that we just talked about. Okay, and we're going to go to the analysis tab. And I'm just going to jump all the way to the end just to find out whether register A has the right value. So the last time I updated is 0. This is for main itself returning a value of 0. but right before that, it got a value of 3, which is from the ABS subroutine. So now the question is, how do we know this is from the ABS subroutine instead of just some random code, that I wrote that just accidentally, put a 3 into register A? Well, we look into location 13, 13, and we look up the assemble tab. And in the assemble tab, we look up location 13, which is right here, and it is corresponding to the increment A instruction of the source code. And as I said, that instruction completes 2's complement of register A. So yes, so the code got the right value because of the correct implementation. So there we go. So I'm not sure whether this is answering Omer's question or not, but it should, because how we push arguments on the stack does not depend on where you are making that call. So you can be making that call inside the very same subroutine that you are trying to call, which is a recursive call, but the process is exactly the same. Oh, okay, gotcha. Well, okay, you have to first access a value first before you can. Okay, let's just say that the argument is a pointer, so you still have to access the quote-unquote value of the parameter first, and that value turned out to be a pointer. So you need one additional dereference to get to what that parameter is pointing to. I don't have it with me, because I don't usually keep my sample programs. But for those of you who kept, you can always watch the video again and just kind of get that code, or sometimes I might even upload the program. But the way I did string copy, you might want to look at the trace of string copy. And I'm going to do the exercise here with this specific program, just so that you guys can try to replicate the same process as you try to learn what is happening on the stack. I sent 2 announcements related to the 2 programs that you need to write. So, but to understand what is going on the stack, it's really helpful to pay attention to column C, because this is where we can see the changes of locations on the stack. For the most part, I don't use global or static local variables, with the exception of traverse. Traverse does have the 5 structures as global variables, which means they're static. But other than that, I don't really want to use global variables. And I use global variables in that case because otherwise the initialization process is going to be taking up a lot of code, and I don't want to do that either. All right, so what you want to do on the side, let me start another spreadsheet on the side, because I'm trying to illustrate what I think you guys can do, but to some of the other programs that I have written, especially the ones that are recursive. Let's see. Right, I need a spreadsheet. There we go. All right, so in the spreadsheet, what you want to do is to basically specify locations in memory. So my typical way of doing this quickly is to use formulae to give me all the addresses in decimal, and then we use dec to hex to convert those into hexadecimal. And we like to look at things from the hexadecimal perspective only because that's how the trace analysis is going to do. All right, and now we want to kind of keep track of what is happening on the stack. So what I just did was really just to set up the overall structure. So now we can see how the stack pointer got decremented to FF, and then the location of FF is getting a 0.9. And then what you want to do, okay, if you're doing the same kind of exercise, oh, okay, so it doesn't like. Okay, I'm just putting a quote in front of everything, so this way it doesn't treat it as a number. Otherwise, the justification is not going to be consistent. So the next thing you want to do is the most important part, which is you explaining what this is and who is doing it. Okay, so I'm just going to prompt the question here: who did this, and what is this value on the stack? Okay, so you have to kind of keep asking those questions. The next one is FD. So we pushed a value of FD on the stack, and then we pushed 2, 1 on the stack. Oh, okay. This is what I mean when I said the justification changes when you have numbers and strings mixed up. And then FD is maintaining that's the last location we use on the stack. So basically ask exactly the same 3 questions. And not only that, okay, you also have to pay attention to register D. When we put 09, FD and FD and then 2, 1 on the stack, that portion is not kind of too difficult, because we can clearly see that in this particular sequence in column C. What gets a little bit more interesting is how register D backs up. So you can see how register D backs up to FE at this point. So you have to make a note of what is happening here. Why are we changing the stack pointer? What is going on? And then it incremented again to FF. So once again, you have to ask what is going on. Okay, what is the context that causes the stack pointer to increment? And one more time is over here. Now you already know what instruction did that, right? Because when you look up, let's just say when it incremented from FD to FE, you already know that the instruction on at location 15 was the one that did it. Okay. In other words, you can find exactly what instruction in your program, and in this case, it will be the instruction at location 15, which is the increment D on line 26 of the program. So you already know which instruction did it. The question is, can you explain what is the purpose of doing this? Okay, so that's kind of how I would study for the exam, is to go through all of the sample programs that I have written up to this point and really take a close look at the trace, which is known as the analysis tab, and try to explain all of the operations. Now this is already a shortcut. What I really want to suggest, especially for people who may not be fully understanding everything, is really just to look at every single instruction and ask, what is this? Oh, this is just a no-op instruction. It is needed because there's a bug in Logisim. Without this, it's not going to trace correctly. Okay, that explains that one. What about this instruction here, 01? What did it do? Well, we know what it did because it put a 0 into register D. So, okay, so I know what this is for. Okay, the register for the stack pointer may not be initialized, and we are just making sure that it is now initialized. What about the instruction at 03? What did it do? Well, it just loaded the value of 09 into register A. Okay. Why did it do that? Why, right? So in this particular case, it is because the code that eventually ended with a halt instruction, it is calling main, and this is the return address. In other words, when main is done, it has to come back to location 09, which is where we will find an additional increment D. Nope, I take it back, which is exactly where we'll find the halt instruction, because you can see at the end of the execution here, it ended at location 09, which means location 09 did have the halt instruction. How would you read cell B6? Okay, so let's go to B6. So B6 is an artifact that that doesn't make sense. Okay, yeah, so this is an artifact, and so is this. It is an artifact because let's see, because it's an LDI instruction, right? So as an LDI instruction, if you go back to the microcode for the LDI instruction, you probably remember that there is a place where it incremented the program counter. And that triggers a transition of which location is reading from. So this is basically reading the next opcode. So the opcode at location 05 is EF, and that would be the opcode corresponding to decrement D. So that's an artifact. It's not it's not supposed to be here. It's not supposed to be significant, but because we incremented the program counter, which caused a transition to the registers and also the contents that we are monitoring, so Logisim creates a log entry for that particular transition. And my code for the analysis tab here would also interpret that and say, hey, the program counter changed, so I better log that in column B because it seems like a read operation from RAM. So that is why we have these artifacts here, because the program counter was changed as a part of the LDI or JMPI instruction. So both of those would actually do this too. All right, cool. All right, excellent. So this is how I would treat the programs. Okay, the sample programs, really kind of go through those by line, instruction by instruction, opcode by opcode, and particularly note changes to the content of RAM. So that would be column C, as well as changes to register D, which is going to be column D. Because those are specific to those are stack related operations, and stack related operations plays an important part of the implementation of C and C++ code, which is basically what you'll be tested on in the final exam. All right, so I think I probably sufficiently answered Omer's question. Any other questions? No questions, really. Well, if there are no questions from you guys, I am going to give myself a question, which is the implementation of, what is it? Tower of Hanoi. Okay, the Tower of Hanoi problem. And we're going to do an assembly language implementation. But how do you know it works, right? Okay, so first of all, let me just refer to you what is the Tower of Hanoi. What is the problem that we are trying to solve? So you just have to search in Google and say Tower of Hanoi. It has its own Wikipedia page. And an animation too. I mean, if you just kind of look at the animation, this is how a simple case of 4 disks is solved. All right, so let me just kind of first describe what the problem is, and in this class, I'm not going to give you the problem and ask you to write the code to solve it. Okay, I might give you the C code. Okay, so I will already have a C implementation of something, and your job is to convert the C code into assembly language. So you're not going to create a new algorithm. You're just going to be implementing an existing algorithm that's already specified in C and turn it into a TTP-ASM program. So that's going to be your job. All right, so let me describe the problem first. So the problem is we have 3 poles, and the job is to move all the disks, from the first one to the last one here. But there are some restrictions, because someone is going to say, well, we'll just go ahead and lift the entire stack, move it over here, and drop it in, and we're all done. What is so difficult about this? No, you have some rules. Okay, so the rules are you can only move 1 disk at a time. All right, so you can only move 1 disk at a time, and the solution has to maintain the largest disk at the bottom and the smallest disk at the top. Okay. And some of you are thinking, but Tech, you already taught us the construct of a stack, right? So we basically pop the smallest one over here, pop the second smallest one on top of that, and so on. So now we have the reverse, of the entire stack over here. And then we'll do the same thing, take the largest disk off of this pole, put it over here, and do it to the rest of everything in this pole, and we're done. Okay, so that doesn't sound too bad, okay? Well, we cannot do that either because there's a second rule. The second rule is you cannot put a larger disk on a smaller disk. So there are two restrictions here. One is you can only move one disk at a time, and the second one is you cannot place a larger disk on top of a smaller disk. So the problem can be solved by, the algorithm is already here. Okay, so there's a recursive solution, and this is the pseudocode of the recursive, solution. And here's a not so much animation, but a illustration. Let's call this the manga version, okay, of how to solve the Tower of Hanoi problem. And if you look further online, you can find the implementations in C. So for those of you who like to Google everything, like myself, okay, there's nothing wrong with Googling everything as long as you really read what it is and understand it. So we're going to go to Google and look up, C implementation of Tower of Hanoi. And there should be like plenty of these examples, okay? So here's one, written in. That's the approach. Where's the C code? Come on. I'm getting impatient. There we go. So there's the C code. Okay, so it's nothing mysterious. The question is, how do we keep track of how can we show all of the actions, right? What are we moving from which pole to which pole? That is going to be tricky. So I'm just looking at the time here and see if I actually have enough time to illustrate this. Looks like I do, even though it might be a little bit pushing it. So we'll go ahead and do this Tower of Hanoi thingy. All right, so the function is going to be a void function. Oh, come on, void function. And we call it Hanoi. I mean, if you guys want me to address some other issues, please, tell me. Instead of doing this, we would like you to do blah blah blah. Okay, but if you do not have any specific thing for me to go over, I'm just gonna talk about this. All right, and on next Tuesday will be. Oh, okay. Could I give us the answer to the final exam? Well, that's something that I cannot do because I don't even have the questions yet. Ask me like 5 minutes before the final exam. I might be able to answer that. Yeah. All right. So unt_8_t. We'll call this is the from pole. Okay. uint8_t. This is via. Through this one. This is the utility pole. It is not part of the source, not part of the destination. And this is the pole where we want to move everything to. And I'm going to do something like this. Okay, it's called uint8_t double asterisk. Yeah, we need double asterisk here. We call it PPTR, pointer to a pointer. And that's basically how we're going to print things. Okay, that's how we're going to print things. All right. This is going to be a recursive algorithm, which means the first thing we need to do is to say, we also need n because we need to, we need to know how many. Let's see. We need to keep track of a count. And how are we going to do that? Let's see. There's an n that has to be a parameter. Okay, uint8_t. There we go. All right. All right. So when n is 1, which means the problem that is given to me only has one disk to move, then I can stop the recursion. So if n equals to 1, it is one case. Otherwise, it is the other case which involves recursion. So when n is 1, which means I'm only asked to move one disk from the from pole to the to pole, then I can just I can just move it, right? Because and this is based on the assumption that all the disks underneath, they're all smaller, okay? And to prove the correctness of the algorithm is a whole different thing. We're not going to address that today. So in this case, I'm just going to move one disk from the from pole to the to pole. There we go. That sounds like a Vulcan name. Anyway, so now we are going to specify, how do we remember this? Okay, so we will do some really tricky thing. PTR plus plus equals to from bitwise OR with 2, and then we shift it 4 times. There we go. All right, so we're going to take up 1 byte, okay, to remember that we performed one operation, moving a disk from the from pole to the to pole, and we're chopping a byte into 2 parts, into 2 what we call nibbles. The lower nibble is going to specify the number or the ID of the from pole, and then the upper nibble is going to specify which pole we are moving the disk to. So this is a very crude way of just kind of keeping track of all of the operations. All right, what if n does not equal to 1? What if n is greater than 1? Well, in that case, we are going to have to use recursion. So the first thing we need to do is to call Tower of Hanoi again. And we want to move from the from pole using the to pole and to the via pole n minus 1 disks, and pass the same pptr. And I used the wrong name here, so it's supposed to be pptr. So after all, this program does have one significance compared to what you need to do for your homework assignment, because your homework assignment has something that sort of resembles this line. So it's going to come in handy. All right, so there we go. And then we will use Tower of Hanoi again. This time we go from the from pole through the via pole to the to pole, the remaining disk of the entire stack. So there's only 1 that we need to move this time, and we don't need to dereference here. I'm just passing the parameter along. The type itself is a double pointer, but I don't need to dereference it twice. Okay, so I didn't make a mistake here. All right, so now what do? Now we use the n minus 1 disks on the via pole, using the from pole as the temporary pole, and then using the to pole as the destination. And we're going to move n minus 1 of those, and then pptr is passed as is, just like that. Okay, so that's Tower of Hanoi, and we'll go ahead and write the main function to kind of work on this. All right, so the thing about the Tower of Hanoi is if n equals to 1, there's only 1 move. When n equals to 2, it'll be 3 moves. When n equals to 3, there will be 7 moves. In other words, the number of moves is proportional to, or is exactly, 2 to the power of the number of disks minus 1. So that means we can't really TTP only has 256 bytes, and that's including everything that we use for opcodes as well as the stack. So we can't really go too far, go too much on this one. So we're going to say uint8_t buffer, and we'll go ahead and define buff length to be, I don't know, 15 is good, I suppose, because that will handle up to 4 disks. So we'll use buff length here, and then we'll go ahead and call the Tower of Hanoi problem or subroutine. So this time, I just need to use numbers, to designate, they're basically just IDs, for the from pole the via pole, and then the to pole. So basically 0 is representing one of the poles, 1 is representing the middle pole, and then 2 is representing the right pole in the picture representation that we saw earlier from Wikipedia. And we'll say originally we have 4 disks, and then we'll pass. Oh, okay, I need a pointer here as well. So this part does resemble a lot compared to what your assignment needs to do. So that's a gigantic hint of why this might be helpful to you. Alright, so there we go. So pointer is initialized to point to the first item or the first element of buffer, and then the address of pointer is being passed along to the Tower of Hanoi subroutine the first time, you have the non-recursive call, and then after that we return a 0. Alright, I have to look at the time because I got about half an hour to actually implement the assembly code. But before we do that, we really need to test it first, just to see whether the C implementation works or not. So this is the other thing, the other tip that I have for you guys when you're working on the homework assignment. You really need to understand what the C code is doing first. So that means, use GDB, okay? Use online GDB or GDB or VS Code or whatever IDE that you would like to use to try to understand what the C code is doing, what is being stored in the variables, what pointer is pointing where, and so on. So you really need to fully understand the C code first, because without understanding the C code, you cannot debug your assembly code because you do not know what it is supposed to do. So you have to kind of keep track of the C code. You can always simplify the code. Okay, so instead of for Fibonacci, for instance, so instead of passing an argument of 6, okay, try 0, because 0 is non-recursive. Try 1. 1 is non-recursive. Try 2. 2 is recursive, but is minimally recursive. So you want to reduce the complexity of your test cases to make sure that your program does work. And it also makes it easier for you to kind of investigate what the C code would do in those particular cases when you're only using 0, 1, and 2 as the test cases for the Fibonacci program. For traverse, I already made some suggestions as to what you can do to simplify the test cases. So instead of using N1, which is the most complex test case, because it does recursion and it goes back and forth a little bit, try 0, which is the null pointer. Okay, if you pass the null pointer, it's supposed to return right away without doing a single thing. So you got to make sure that your assembly code is doing exactly the same thing as the C code first. So that means you need to modify the C code to try out the simpler test cases first, figure out what the C code is doing with the simpler test cases. Then you can go ahead and do it, try to implement the assembly language code and do it step by step too. Okay, so so just a little bit of tips to implement the programs in assembly code for the homework. Alright, so there we go. We have the Tower of Hanoi problem. I'm just going to put a breakpoint on line 24, feeling confident that the program is supposed to do what it's supposed to. So we'll go ahead and put a breakpoint on line 24, run the program, and now we'll say what is in buffer. Okay, so you look at this and it does not look right to me, unfortunately. The reason why, okay, so we want to use use a /x so that everything is printed in hexadecimal. So we can see that it's moving from disk 2 to disk 1, and then these are unreasonable. These are simply not right. Yeah, so they are not right here. So these are not supposed to be FFs, because they should always have 0, 1, or 2 as the upper or the lower nibble. FF is using 15 as both, so that would not be right. So the program did not work. Okay, so embarrassingly, the program did not work, but that's okay, because as I have told you guys already, this gives me a chance to show you how to debug a program. And this time it's not an assembly language program. This one is just a C program. All right, so let's check out why this is not working. All right. So PPTR++, I think it has to do with the order priority, because without the parentheses, it is actually going to increment the parameter, and that's not what I want. I want it to increment what the parameter is pointing to, so that is the problem there. Okay, so Omer said run fib and traverse in online GDB. Yeah, that would be very helpful. One thing I don't know if we have time for. Oh, okay. Absolutely. Okay, so let me just run this first, and I can finish up this program on my own, and then make another video to show you the answer. But at least I want to show you whether it works or not, and then we can move on to what Omer suggested, which is actually what I suggested, but I forgot about it. I wrote about it, and then I forgot what I wrote. So let's put a breakpoint at line 24, run it, print print/x for hexadecimal buffer, and this time it is correct. So basically what it said is, the first thing we did was to move the top disk from PO 1 to PO 0, and then excuse me, the other way around, because it moves from the lower nibble to the high nibble. So it moved from PO 0 to PO 1, and then from PO 0 to PO 2, then from PO 1 to PO 2, and then from PO 0 to PO 1, blah blah blah. This is PO 2 to PO 0 because the leading 0 is not shown, and so on. So this looks about right to me. So I'm not gonna spend too much time on this one, except for one more thing. There's always that one more thing, right? So if I look at pointer minus buffer, that will tell me exactly how many moves has been made, and that should be 15. There we go. Okay, so the algorithm actually worked, but instead of continuing with this program, I'm going to show you those two programs that you're supposed to write. All right, so I'm going to start with traverse. Okay, so traverse is the more difficult one, and I need to go find the C code, which I think is shared, if I remember correctly. So it's already on online GDB. So there we go. And we go to my projects. And traverse. Yeah, there are probably multiple traverse here because I do the same thing every semester. There we go. And this is this the right traverse? Yeah, looks right to me. All right. So the way you want to implement this program in assembly language is step by step. Okay. I cannot overemphasize the step-by-step portion. The reason why you want to do it step by step is because if you write a whole lot of code and it didn't work, and I can tell you it is not going to work, okay? Because when I write code like this, it's not going to work the first time either, okay? So you really want to make sure that it's easy to debug and find out why the program is not working. So the first thing you want to do is to analyze the subroutine that you're supposed to implement, because main is already given to you. There's not much to do with main, except for changing the parameter. Okay, but you change the argument from main just so that you can find out whether traverse is working or not. Okay, so how do you decide how to test the program? So when you test the program, you want to understand what traverse is actually going to do. But the simplest way to figure out the simplest test case, okay, the simplest test case is to say, oh, so if pointer is null, traverse is going to do absolutely nothing, right? So that would be the first version of your program to try to write, is to ignore and basically don't do anything about these 3 lines. Okay, just leave it blank. Okay, substitute it with a bunch of no op instructions or a halt instruction. Okay, doesn't matter. Okay, it's just that you're going to test it with a null pointer. So having a null pointer here means in main, when you call it, you have to change this to 0. Just 0 is fine. Okay, null, N-U-L-L, all uppercase, is really a fancy way to say 0. That's basically all it is. Okay, it's just 0, except the type is a pointer. So that will be the first test case. Okay, so let me just go ahead and do exactly that, right? So put a 0 here. Save the code. It already knows it's a C code because once you save a project, it knows what language it's supposed to be in. So now we go to we put a breakpoint here, and then we click on debug. And there are two things you can check. You can double check. So we'll go to debug and run the program. Unfortunately, the contrast, some of the font has a very poor contrast. Not sure whether that can be changed or not. Probably can, but not sure how. All right, so it did get into the subroutine in Traverse, and because PTR is a 0, it should skip everything here and just return right away. So we want to verify that behavior in C first. So now we single step through it. Okay, so single step. And sure enough, it did not do any thing in the then branch, and then it returns back into main. So when we get into main, you can verify whether the program did it correctly or not by checking whether PTR is the same as buffer this time. So you basically just say print PTR equals buffer, because GDB is smart enough to recognize basically all the expressions that you can type in C and C++, so it can actually compare a pointer to an address, and it will tell you whether it's true or not. In this case, it is true. Okay, so this is the first thing you need to do, is to check that. All right, so next, what do you do? What do you check? So the next thing you want to check is not to use N1, N2, or N3, but to use N4 or N5. They're equivalent. The reason why you want to use N4 or N5 is because both of these, okay, N4 and N5, has the L and the R members all being zeros. In other words, it will get into this code here, and it will perform one level of recursion. But that one extra level of recursion will return right away. So this is as simple as it can get, when it is a non-trivial case. All right, so we'll go ahead and test that. Okay, so now we are changing traverse from main. Instead of using a null pointer, we're going to say the address of N4. Now the address of N4, because N4 is a global variable, all global variables are by their very nature static as well. So that means in the assembly language implementation, the label N4 is really representing the address of that particular structure. So we just have to push N4 as a label onto the stack, and that's how we call traverse with the address of N4. And that part is done already, because the assembly language code that I gave you is already calling traverse with the address of N1. So all you have to do is to change N1 to N4, and now we have the simplest non-trivial test case. All right, so I'm going to save the code and debug it. There we go. So debug with the same breakpoints, okay? Because it's very important to use the breakpoints and single step through the code, just so that you know how the code is supposed to work. All right, so now we have, oh, I need one extra breakpoint. Well, it doesn't really matter too much, but I'm going to put a breakpoint here, just so that we can see that it's calling from main. It's going from main to the first invocation of traverse. All right, there we go. We say run. All right, so we are now on line 40, which is calling traverse from main. This is the non-recursive call of traverse. So if I single step through this, it's not going to be a big surprise. We'll end up on line 21. There we go. We are now on line 21. which is the brace before line 21. Single step one more time, and now we're on line 21. You can see pointer is a whole bunch of hexadecimal digits. Well, all you need to understand is it is non-zero. Okay, so as far as it is, as long as it's non-zero, this is gonna PTR is considered true, because in C, anything other than 0 is considered true in the context where we need to know whether it's true or false. So if I single step here, it should go to line 23. There we go. So when we are on line 23, it is a unconditional recursive call to traverse. But you might want to know what it is going to call traverse with. In other words, what is the value of the L member of the structure the PTR is pointing to? So we can always say, print asterisk PTR, which dereference PTR, and it will show us the entire structure. So when it shows the entire structure, it shows that the value is 4, L is a null, and then R is a null as well. I know it's difficult to read because of the color scheme, whatever, I don't understand why they chose this particular color scheme. It's probably the default, but it's just a little bit harder to read. Not sure whether you can change it or not. I'm just taking a quick look to see if there are any configuration that you can do here. Pretty sure there's one. There has to be a way to change the contrast, but just trust me. L is null, R is null as well. Array is the same, okay, because you can see how this array is passed as is to here and also as is here. Okay, so now when we single step, we should go back to line 20 again, and then to line 21. So there we go, single step, and you can see how we are now in traverse again. And if we single step one more time, we'll be at the entry point of the conditional statement. So right now, I'm going to show you something that is going to be helpful, not only in this class, but also in general when you're writing programs in C or C++. Not sure whether I have shown you this already. It's called BT, or backtrace. Somebody just rang my doorbell. Not sure, but no one is answering the door. I might need to go get a door. Anyway, if it rings again, I'm gonna go check out who's at the door. Okay, I have to go. Sorry about that. All right, I'm back. Well, I hope you guys enjoyed the short break. All right, so this is backtrace. So backtrace is really helpful when you're debugging a program, especially when it is recursive, but it is helpful even with non-recursive programs. It shows us, that main called traverse, and then from traverse, it also called traverse. So you can tell how many invocations of traverse we have on the stack. Now, this is also important from the perspective of your program, because now you can understand that the call frame of main, the call frame of the first invocation of traverse, and the call frame of the second invocation of traverse, they should all be on the stack. And if you already know what the call frame of traverse should look like, then you have some expectation of what you should see in terms of the content of RAM. All right, so this is really important because it gives you an idea of what should be in RAM at this point of the execution of this program. We're at the entry point of the second invocation of traverse. All right, so I'm really hoping that you guys are still with me because this is really important. I'm trying to show you guys how you can test your program not only in C, but to understand what the equivalent would look like in TTP-ASM. All right, now since we are now in the second invocation, and we can also tell that PTR this time should be a 0, so that means we should skip the then statement this time around. All right, but I just mentioned something where some people may say, but I have no idea what a call frame is or how it should look like at this point of the program. Well, let's go ahead and take a look at that, shall we? All right, so I'm going to show you first, what a call frame is. It's going to look like for Traverse. So in order to do that, we are going to look at the prototype of Traverse first. Now, the prototype is important because now we know what the number of parameters, as well as the types of the parameters, as well as whether there are local variables or not. Okay, so that's really important. So we know the call frame of Traverse is going to have array, which is a parameter. The second parameter is going to occupy the highest address of the call frame. And then next byte down is going to be PTR. Now, we're only counting bytes here because the TTP is a 8-bit processor, so every single address that you need to store is going to be only 1 byte wide, which makes things a lot easier to count because everything is just 1 byte. After this, we have the return address, and that's it. Okay, this is the call frame of a Traverse invocation. So now the next question is, from the perspective of your program, how are things going to look like? Now that depends a lot on how N1 to N5 how they're defined, as well as how we order the local variables of main. Because basically you also have to understand the call frame of main, because that is going to be the first call frame. And then below that will be the first invocation, the call frame of the first invocation of Traverse, and then below that will be the call frame of the second invocation of Traverse. Okay, so let me just kind of pause here because I have that sinking feeling that I have lost the entire class. So I'm going to have you guys to ask me questions of what I have just mentioned up to this point. Alrighty. Well, okay, so getting back to why the call frame should look like this, it has to do with... Alright. Yes, that is why I record all the lectures, is so that you guys can watch it again. But why the call frame looks like this has to do with the agreement between the caller and the function being called. The agreement is we push arguments backwards. So the last argument is pushed first. That means it has the highest address. And then the second argument, the first argument is pushed next. So it has the second highest location. And then we push the return address. So why is the item pushed first having the highest location? That goes back to how the stack is used. Okay, so that's a very, very ancient, old topic, and I kind of feel that it's really crucial to have that already understood at this point, because otherwise, there will be a lot of catching up to do. I'll just put it that way. All right, so from the main perspective, so I think the main program that I gave you allocates for PTR first and then buffer. Excuse me, I take it back. It allocates for buffer first and then PTR, so that buffer has a higher address compared to PTR. So this is the call frame for one invocation of Traverse, and then main is going to have a 0 argument coming from whatever code is calling main, but it does have local variables. So that means the return address is going to be occupying the highest address of the call frame of main. And then next we have buffer. So buffer is going to take up 6 bytes. So we have buffer 5, buffer 4, buffer 3, buffer 2, oops, buffer 1, buffer 0. So these 6 bytes, belong to buffer as a local variable, and then PTR is below that because I personally prefer to. Oh, or is it the other way around? It's the other way around. Sorry, let me fix that. Uh, the reason it has to do with I prefer to, and yes, click yes, and then oh, it didn't like that. Let's do it one more time. This time, Control X, and we just want to move everything down by 1. There we go. So the reason why it's like this has to do with whatever is declared first needs to have a lower address. So I'm trying to follow that convention, which is not really a compiler or a language specified thing. It's just this way it maintains there's a particular order to how I declare the local variables. Alright, so this is the call frame of main, which consists of all the arguments, which is 0 in this case, the return address. Every single subroutine has a return address. It has to know how to get back to the caller, and the local variables. So in this case, the local variables make up the bulk of the call frame of main. So how is this useful? Well, it is useful because now you can kind of expect what your stack should look like. So I'm going to use that trick again to take a look at the memory locations. So this is this location -1, and we'll just do a bunch of these. There we go. All right, so which function is called first? That should be a pretty, there we go. Oh, my webcam is blocking. There we go. I can always just turn it off. I'll turn it off. There we go. Click. Okay. So, who is called first? Which subroutine is called first? Main. Very good. Okay, excellent. So we got the answer. So that means this call frame here, this entire, I wouldn't call that a structure, but this format, okay, this template is, oh, okay, Control C for copy and paste here. So that's how the stack is going to be used initially. Okay, when we get to main, main has these locations to play with. When main calls traverse the first time, it's going to have this structure because this is the call frame of traverse. So this is going to be how the next 3 bytes are used. Now, in this specific example, it's going to perform one more level of recursion, which basically means these 3 bytes would be used by the second invocation, which is the recursive invocation of traverse. So what that means is the stack should go as low as location 242, and we can kind of expect where we can find PTR, where we can find the array of buffer, where we can find the parameters of each invocation of traverse. So that also means, okay, so let me use the hexadecimal representation here. So we have dec to hex this particular value, and then extend it all the way down. I'm just going to overdo it a little bit here, and kind of narrow the columns. So now we have a fairly good idea of where things are supposed to be located, and that is important because if you do not see the address, if you do not see the address of pointer at location F7, and by the way, according to this, what is the address of PTR pointer, which is a local variable of main? Can someone tell me in hexadecimal where I can find PTR of main? Well, okay, yes, I did say hexadecimal, but close enough. That's good. Yes, FE or 256. Okay, FE in hexadecimal or 256. So if I don't see FE, which is the address of PTR here, I know the program is not working. Okay, something did not go right, because that is, so this is the address, but if I look at the value at that location, it is supposed to be the address of PTR, which is in this specific case FE. So if I look at the trace in the analysis tab, and it wrote some other value, some value other than FE to location F7, then I can probably ask myself, okay, something did not work right. Okay, why is it not getting the value of FE at location F7? Okay, so this is how we debug the program. Okay, it's really step by step, and this one, is check. You can check this one, even if you were to use 0 instead of N4, the address of N4, when you call traverse from main. So that would be the first thing I check in the TTP ASM implementation, is really just to make sure that we got the right items on the stack, because that's really kind of important. What about this PTR? Oh, I think, did I mess up? Nope, I did not. Okay, I did not mess up. So if I did use N4, in this particular case, then I should see the address of N4 here. So as far as this is concerned, this is the address of N4. But when we perform the recursion, this would be the same, which is the address of PTR. So the address of PTR is always the value of the parameter array, and it should always have the bit pattern of FE. Excuse me. But the second invocation is going to have 0 as PTR. Why? Because the L member, okay, let me go back to excuse me. Because the L member of N4, so if you look at N4 here, the L member is that the first item? Yep, the first member. The L member of an N4, of N4 as a struct node, is a null pointer, and that's what we passed. Oh, wrong, wrong sheet. Oh, where is the one that I was looking at? That one. There we go. Okay, so excuse me for the confusion here. All right. So this is what you should be seeing. Now the actual address of N4 depends on the code, because if you try to put your traverse code ahead of the definition of the global variables, it's going to change it. But the value of a label is easy to track down, so you should be able to track it down. But this one should be just a 0 because it's a null. So this is kind of how I would test the program, is really to understand what should be on the stack. Do it, you can't really do this for very complex test code or test cases, but you can do it for simpler test cases. So I would just kind of do it for simpler test cases first, just to make sure that your code is working. So are there any questions, comments about how to go about basically writing and checking and debugging the traverse code? All right, well, I'm glad at least one person finds it useful. All right, so let me just kind of check the TTP ASM code and make sure that this is the right order, okay? Because I'm not 100% sure this is the right order. And that part is in the announcements. And if you have not checked out the announcements for the additional resources for the traverse code and the additional resources for the Fibonacci code, that's probably the first place I would go. In fact, I would check all of these announcements and make sure that you have read every single one of these. And even if you have read every single one of these, you might want to reread some of these if you just want a refresher of what I am suggesting how to go about writing these programs. All right, so I am going to why PTR has a higher address. Okay, so let's check the assembly language code because main is already done. So let me see. It's a traverse -1 tt.ttpsm. All right, so let me go there first in here. All right. All right, so let's take a look at how the labels are defined. So right here, and I got it flipped. Okay, I got it flipped. My bad. So buffer is at the lowest place, and then PTR is at the higher place. So that's why Omer is asking the question because the way I define the labels here is opposite to the spreadsheet that I have been showing you guys. So instead of doing this, oh wait, it is actually correct. I take it back. Okay, so I know I'm confusing you because I was confusing myself first, and I recognize that. Anyway, this is correct, but this is good, okay, because now we actually get a chance to double check everything. Buffer has an offset of 0 to relative to where the stack pointer points to. So that means when I get to main, after everything is allocated, the stack pointer should be pointing here. It should be pointing at the first byte of buffer, and that's why buffer has an offset of 0 from where the stack pointer points to. Buffer has 6 bytes, okay, so 0, 1, 2, 3, 4, 5. So PTR is 6 bytes away from the beginning of buffer, and that's why PTR is supposed to be here. Now on top of that is the return address, and that has to do with main is now treated as a normal subroutine. So this is how we push the return address of calling main on the stack. So that's why main is really now just a normal subroutine, which also means in main, at the very end of main, it is supposed to pop the return address and use that to go back to the halt instruction. So I hope this kind of helps out with the confusion, because I know how it sounds, because in order to clarify the confusion, I first confused myself first, and then I went to take a look at the code and go like, wait, hold on a second here. I wasn't wrong. I was actually correct. I was consistent. So there you go. All right. So these are very important concepts, because how you test your code can really affect how much time it takes to implement the code. So let me get back to the C code first, and that would be here. All right, so let me just kind of comment on this line here. The first value you want to test would be a 0, which is a null pointer. So with a null pointer, it should do absolutely nothing. Traverse as a function should do absolutely nothing other than checking whether PTR is null or not, and then return right away. Now, if you give it n5, okay, the address of n5 as a test case, then it will perform one level of recursion. But that one extra level of recursion should return right away because the L and the R member of n5 are both zeros, right? But the question is, if you use n5 as a test case, what should happen to buffer? Okay, so I'm just going to write it out here. It's not going to reflect, when you use the link, it's not going to reflect these changes, simply because, whenever the code is changed, the link also changes. But your link should still link to the prior version, which is using n1 as the parameter. So if the address of n5 is the if the address of n5 is the test case, then you can check your code. Okay, so the way you check your code is ptr minus buffer should equal to 1. So there should be one value put into the array of buffer, and that should be, so buffer bracket 0 should equal to n5 dot v. So the value, well, did I use v or value? Value. There we go. Okay, so this is how you can check your code, is to look for these things in your assembly code when traverse returns. If you use n3, okay, so let's try to take a look at this code and find out what would be the result when n3 is the test case. So if n3 is the test case, ptr minus buffer should now be 2. So the ptr, which is a local variable of main, is going to change. Now the reason why the subroutine traverse can change the local variable of main is not because of the scope, okay? Because local variables only have a scope of the same subroutine or the same block, because we are talking about C here. The way the traverse can change the local variable of main is because the address of PTR is passed to traverse. So traverse doesn't understand the name PTR of main, but it does understand the address of that. It is known as address, okay, array, sorry. So it's known as array in traverse. Array is a pointer to a pointer, in this case to PTR of main. So in this case, buffer 0, the first thing is going to be, so now you have to be careful, because if you're dealing with n3, the first item is, it will also do a recursion to n5. So it will basically put the value of n5 into the first item in the array, and then the second item is going to be n3's own value. So the second item in buffer should equal to the value of n3 itself. So all of these you can test using GDB. So let me just kind of show you what I mean by that. Okay, so if I use n3 here, oh, I just typed the wrong key. There we go. Control S, save the code, and go ahead and debug it. So I want to debug the code just to show you, by the time we get to the return 0, what's going to be in buffer and what is the relationship between PTR and buffer. So if I subtract buffer, which is just an address, from PTR, which is a variable containing an address, it should be 2. So we'll go ahead and run the code, continue. Oh, okay. Run first, continue, 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 continue. And now we are ready to return. All right. So when we are ready to return, we should see ptr minus buffer to be 2. And if we say print /x buffer, we should see the value of n5 first, which is a 9, followed by the value of n3, which is a 10. But since we're printing it in hexadecimal, that would be an A, because the digit A in hexadecimal means 10. So that should be what we are expecting. So we have 9 and A in it. So the program did perform as I expected. And this is how you can debug your program as well, because if we already have a map of the memory here, then you can always compare the content at this location FE and compare that to the actual value of FB, and that difference is what I have just printed here, which is PTR minus buffer. And then the content, which is what is displayed here, the first item is 9, the second item is A in hexadecimal. That is also easy to verify, because now you can look at the content of this location. That should be a 9, 0, 9, and this location here should have a content of 0A. So this is how we can, this is me trying to help you to understand how the C code works, how to observe, how the C code is working, and then compare the outcome of your assembly language code to the outcome of the C code. Because even though the architectures are entirely different and the actual addresses of where you can find these things are entirely different, in the C code it's easy to find because you can use your C syntax to say, okay, tell me what is at location blah blah blah, or tell me what is the difference between PTR and buffer. But in assembly code, because we have the trace, because we have the analysis tab, we can also do about the same thing. You just have to kind of put all of the content in all of these locations back together into this format. And that you can do by tracking down column C of the analysis tab. So you can basically reconstruct the content on the stack by looking at how we wrote values into the stack as your program ran. All right, so oh, we are 15 minutes over the intended end time of the lecture, but since we don't have we do have a lab today, so I'm gonna have to give you guys some time to do the lab. I'm not sure is this helpful or not, but I think it's really crucial, really important stuff. Are we okay with this or not? Okay, excellent. All right, so I will release 2 lab stuff for you guys to do. Just get rid of the lab. Well, that is not going to help with the final exam, is it? Because the intention of the lab is to help you with the concepts. Okay, so I'm going to first check and make sure that all of these are multiple choice or that sort of answer. Yeah, so these are all they shouldn't take much time. There's no code that you have to write. All right. All right, there we go. And I will show the answer at 9. Let's make it 10:05 p.m. I'm going to give you guys some extra time. So for the first lab, the access code is struct. There we go. And we'll make it due at 10:05 p.m. So the intention of this lab, or these 2 labs, I'll give you 2, is to gain a better understanding of structures, which is important. That is really important because the Traverse lab works a lot with structures. So that's the intention of this lab, and I'll give you the other one, which is making simple use of struct here. This one has 10 points, but it's similar to the other one. And let me just kind of double check and make sure that there's no code to turn in. Okay, here's question. This one I may not want you to do. Okay, so only the first one. There you go. So you have all the lab that you need now, because this one does require you to turn in a program, which is not what I intend for you guys to do tonight. So there you go. Only one lab tonight, and looks like a fairly simple one. And it's due at 10:05. That's it. That's it for tonight. I will still be here if you guys want to discuss, the process of writing the code and to debug the code. All right. Any questions before I sign off from the interactive channels? Looks like there are no questions. Cool. All right, so I'm gonna sign off here, and I'll be back in a few minutes. Oh wait, okay, Philip is typing. Let me just make sure that I can address that first. Oh, okay, yeah, you guys too have a nice weekend. But yeah, work on these programs. The key is to figure out how to write the programs. Okay, because if you write the program in the right order, give it the right test cases, it's not going to be super duper difficult. But if you really try to write the entire subroutine first and then test it, that would be like super hard to debug. I mean, you'll be spending like hours and hours and hours. So that's the key. I will try to see if I can post some additional instructions as to how to proceed, how to write the code. Um, but I have written for the most part, all that I could think of. But I'll see if I can write some more. Okay, all right. Bye.